Hello friends, welcome to my lecture on initial value problem for Quasi-linear first order equations. We know that a first order Quasi-linear partial differential equation is of the form Px by z into partial derivative of z with respect to x, which we have denoted by P earlier, and then plus Qx by z into partial derivative of z with respect to y, which we have denoted by Q earlier, is equal to Rx by z. Now let us assume that an initial surface or a possible solution surface z equal to zx by of the equation 1 can be found. Then we can write this equation z equal to zx by as zx by minus z equal to 0. Let us write zx by minus z as a function of x by z. So fx by z will be equal to 0. Then the partial derivatives of f with respect to x, y and z can be determined. Partial derivative of f with respect to x is derivative of z with respect to x, partial derivative of f with respect to y is partial derivative of z with respect to y, and partial derivative of f with respect to z is minus 1. Now we know that fx by z equal to 0 represents a surface, and del f is a vector which is normal to the surface. So here the components of del f, which are the partial derivatives of f with respect to x by z, are zx, zy and minus 1. So the gradient vector del f is equal to zx, zy minus 1 is normal to the integral surface fx by z equal to 0. The equation 1 can be written as px by z, qx by z, rx by z dot zx, zy minus 1 equal to 0. Let us take the dot product of the vectors px by z, qx by z, rx by z with zx, zy minus 1 equal to 0, then what we get is this equation. So what do we obtain? The vector px by z, qx by z, rx by z is orthogonal to the vector zx, zy minus 1, but zx, zy minus 1 is a vector along the normal to the surface fx by z equal to 0. So the vector px by z, qx by z, rx by z is a vector which lies in the tangent plane to the surface z equal to zxy at each point xy where gradient of f is not 0. Now the direction determined by the vector pqr, that is px by z, qx by z, rx by z, which we are writing in short as pqr. The direction determined by the vector px by z, qx by z, rx by z at each point x by z is known as the characteristic direction. A curve in x by z space whose tangent at every point coincides with the characteristic direction field pqr is called as a characteristic curve. At each point of this characteristic curve, the tangent coincides with the characteristic direction, that is the direction given by the vector pqr. Now the parametric equations of this curve, characteristic curve, let be x equal to xt, y equal to yt, z equal to zt. Then the tangent vector to this curve, we know if the vector is if the curve in the space is given by x equal to xt, y equal to yt, z equal to zt, then the tangent vector to this curve is given by dx by dt, dy by dt, dz by dt, and therefore dx by dt will be equal to px by z, dy by dt equal to qx by z, dz by dt equal to rx by z, because of this, because this curve is a characteristic curve. This curve is a characteristic curve. So at each point of this curve, the tangent to this curve will coincide with the characteristic direction, and so at dx by dt will be px by z, dy by dt will be qx by z, dz by dt will be rx by z. These equations are called as the characteristic equations of the Quasi linear PDE. Now and the solutions of 2 are called the characteristic curves of 1. So the solutions of this equation dx by dt equal to px by z, dy by dt equal to qx by z, dz by dt equal to rx by z are called the characteristic curves of the Quasi-linear PDE. Now assuming that PQR are sufficiently smooth and do not all vanish at the same point, then from the theory of ordinary differential equation, a unique characteristic curve passes through each point x naught, y naught, z naught. So, this is to be noted. If p, q, r are not do not vanish at the same point, then a unique characteristic curve passes through each point x naught, y naught, z naught. Now, to solve the initial value problem for the Cauchy-linear PDE, we pass a characteristic curve through each point of the initial curve C given by the IVP. In the initial value problem, you will be given an initial curve at t equal to 0. So, to solve the initial value problem, we will have to pass the characteristic curve through each point of the curve C. These curves generate an integral surface, which is the solution of the IVP. In the non-parametric form, we can write the equation 2 as dx by p equal to dy by q equal to dz by r. Now, let us look at the method of characteristics or the method of Lagrange. So, the general solution of the Cauchy-linear PDE is, the theorem says that the general solution of the Cauchy-linear PDE P plus QQ equal to R, where PQ are P, Q and R, they are functions of x, y, z. So, the general solution of this Cauchy-linear PDE is phi u v equal to 0, where phi is an arbitrary function, u x by z is equal to some constant a and b x by z is equal to some constant b. They form a solution of the characteristic equations in the non-parametric form, that is dx by p, dy by q, dz by r. Now, let us prove this theorem. So, we have to prove that the general solution of the Cauchy-linear PDE is given by phi u b equal to 0 if u x by z equal to a, b x by z equal to b form a solution of the equations characteristic equations dx by p equal to dy by q equal to dz by r, and phi is an arbitrary function. So, let us see how we prove this. So, if u x by z equal to some constant a and b x by z equal to some constant b, they satisfy the Cauchy-linear PDE, that is p p plus q q equal to r. Then from u x by z equal to a, we see that the partial derivative of u with respect to x, that is u x into dx, partial derivative of u with respect to y, that is u y into dy, plus partial derivative of u with respect to z, that is u z into dz is 0. Similarly, b x by z equal to b gives you partial derivative of b with respect to x into dx, plus partial derivative of b with respect to y into dy, plus partial derivative of b with respect to z into dz equal to 0. Now, these equations must be compatible with 4, this characteristic equation, because u x y z equal to a and b x y z equal to b form a solution of these characteristic equations. So, they must be compatible with 4, which implies that now 4 gives what? 4 is dx by p equal to dy by q equal to dz by r. Okay. So, if these equations are compatible with this equation, then what we will have p into u x plus q into u y plus r into u z equal to 0 plus and then p into v x plus q into v y plus r into v z equal to 0. Now, if we solve these two equations, this and this with respect to for p, q and r, what we will get? P over u y b z minus u z b y equal to q over u z b x minus u x b z, and then r over u x b y minus u y v x. So, this is what we get when we solve these two equations for p, q and r. Now, we can write them in the form of the Jacobian. This is this gives you p over Jacobian of u b with respect to by z, okay, and then we will get the Jacobian of here u b again with respect to z and x, and we get here Jacobian of u b with respect to x y. Okay. So, we can write these ratios in the form of Jacobian P over partial delta u b over del y z, and then del u b over del z x, and then del u b over del x y. So, we get this. Now, differentiating 3, let us differentiate 3. 3 is this phi u b equal to 0. So, let us see when we differentiate phi u b equal to 0, where u is equal to u x by z, u equal to u x by z, and b is equal to b x y z. U x by z equal to C 1 and b x y z equal to C 2. So, when we differentiate this equation phi u b equal to 0 partially with respect to x, what we get? Phi u into u x plus u z into z x plus phi v into v x plus b z into z x equal to 0. And similarly, when we differentiated with respect to y, we get phi u into u y plus u z into q plus phi v into v y plus b z into q equal to 0. So, this is what we get when we differentiate phi u b equal to 0 with respect to x and y. And then when we eliminate phi u and phi v, when we eliminate phi u and phi v from these two equations, what we will get? We will get the determinant of u x plus u z into p, u y plus u z into q, and b x plus b z into p, b y plus b z into q equal to 0. So, this determinant will be equal to 0, and when we solve that, this determinant we get this is equal to 0. So, when we put p for z x and q for z y and solve, okay, simplify this equation, we get p times u y b z minus b y u z plus q times u z v x minus v z u x, and then u x b y minus v x u y, and which we can write in the form of Jacobian as p into del u b over del by z plus q del u b over del z x plus equal to del u b over del x y. And then we can see in view of 5 this equation. Okay. Let us use this equation 4, then what do we notice? This equation will be replaced by P p plus Q q equal to equal to r in view of 5. So, we see that phi u b equal to 0 is a solution of equation 1 if u x y is equal to u x y z equal to constant and b x y z equal to constant satisfy the characteristic equations. Now, let us look at this equation x z x plus y z y equal to z. So, this is of the form x p plus y q equal to z. So, it is Cauchy-linear first order PD. So, we can write the characteristic equations dx by x dy by y equal to dz by z. Now, solving the relation dx by x, there are two relations, independent relations. So, dx by x equal to dy by y gives us ln x equal to ln y plus ln c 1. So, we get x over y equal to c 1. So, this is one solution. We can take another independent relation dy by y equal to dz by z, which gives us ln y equal to ln z plus ln c 2, and we can write y over z equal to c 2. So, we get this is your phi x, this is your u x by z, and this is our b x y z. So, we got two solutions u x y z equal to constant, v x y z equal to constant, which are the solutions of the characteristic equation dx by x equal to dy by y equal to dz by z. Hence, the general solution is given by phi u b equal to 0. So, that means phi of x over y and y over z equal to 0. We can, instead of taking y dy by y equal to dz by z, one can take dx by x equal to dz by z also. So, there are two independent relations, third one is dependent on the other two. So, we can write the general solution of this Cauchy-linear PD as an arbitrary function phi of x over y, y over z equal to 0. Here we have written f instead of phi. Now, let us go to another problem. So, we have a Cauchy-linear PDE of first order. Let us compare this given partial differential equation with the standard form PP plus QQ equal to R, then P is equal to Z into X plus Y, Q equal to Z into X minus Y, R is equal to X square plus Y square. The characteristic equations are dx over p, that is z into x plus y, equal to dy over q, that is z into x minus y, and we have dz over r, which is x square plus y square. Now, let us first consider dx over z times x plus y equal to dy over z times x minus y. Then we can write it as x minus y into dx equal to x plus y dy. R I can write it as x dx minus y dy equal to x dy plus y dx. Integrating both sides, I have x square by 2 minus y square by 2 equal to x y plus some constant, say alpha. Okay. Or I can write x square minus y square equal to 2xy plus some constant plus 2 alpha, which I can write as 2xy plus some constant c, where c is 2 alpha. Okay. So, one solution we have found, x square minus y square minus 2xy equal to constant. Let us find another solution. So, we notice that x dx minus y dy minus z dz, if you consider, then this is x into z x plus y minus yz into x minus y minus z times x square plus y square. Okay. So, these ratios are equal to this. The characteristic equations are dx over p, dy over q, dz over q, which is also equal to this. So, this is equal to x dx minus y dy minus z dz divided by x square z plus x y z minus x y z plus y square z minus x square z minus y square z. So, x square z cancel, y square z also cancel, and x y z cancel. So, this implies that x dx minus y dy minus dz dz over 0. Okay. So, this equal to this, and this implies that hence x dx minus by dy minus z dz equal to 0. When we integrate this, we get x square by 2 minus y square by 2 minus z square by 2 equal to some constant, let us say beta. Okay. So, this gives you x square minus y square minus z square equal to 2 beta, which we can take as say a. Okay. So, x square minus y square minus z square is equal to a. The other solution we have got x square minus y square equal to 2xy plus c. So, I can also write this solution, this one. Okay. This solution I can also write as x square minus y square minus 2xy equal to c. Okay. Now, from this solution, let us say this is 1, this is 2. So, from 1 and 2, if we write x square minus y square equal to 2xy plus c, then what we get? From 1 and 2 I get 2xy plus c minus z square equal to a, or I can say 2xy minus z square equal to a minus c, which I can write as another constant b. Okay. So, one solution is x square minus y square minus z square equal to u, and the other solution we can take as 2xy minus z square equal to b. So, then the general solution is f u b equal to 0, say u is x square minus y square minus z square, and b we can take as 2xy minus z square. So, I can write f u b equal to 0, or I can write as f b u equal to 0. So, we get the solution as f of 2xy minus z square and then x square minus y square minus z square equal to 0. So, this is how we get the general solution of this Cauchy-linear first order PDE. Now, let us look at this equation. This is again a Cauchy-linear equation of Cauchy-linear PDE of first order. So, dx by x times z minus 2y square equal to dy upon y into z minus y square minus 2x cube and then dz over z into z minus y square minus 2x cube. Now, let us look see these characteristic equations carefully. This second ratio dy over y times z minus y square minus 2x cube equal to dz upon z into z minus y square minus 2x cube. If we take first this relation, then we will be easily able to get the first solution. So, dy over y times z minus y square minus 2y cube equal to dz by z into z minus y square minus 2x cube. This is 2x cube. Okay. So, from this what we get, this vector will cancel, we will get dy by y equal to dz by z, and this will give you ln y equal to ln z plus ln c1. So, we get one solution y over z equal to c1. So, one solution we have got, we can take it as ux by z equal to y over z equal to c1. So, one solution we have got. Now, let us look at the other solution. So, we have to choose lambda mu nu in such a way that lambda dx plus mu dy plus nu dz becomes 0. So, what I do is I choose lambda as say 1, mu as 2y and nu as minus 2, then what I will get. So, x times z minus 2y square into x times z minus 2y square, we are multiplying by 1. So, this plus mu we are choosing at 2y. So, 2y into y times this. So, 2y square z minus y square minus 2x cube what we have to try dx over what we have to do minus 2 dz, what I will get, minus 2 z into z minus y square minus 2x cube equal to 0. Will I get that 0? Dx, we should not try this. Let me see, dx upon x over z minus 2y square is equal to, and here what we will take 2y dy minus dz. Let us try this. Okay. So, here we take 2y. So, 2y square into z minus y square minus 2x cube minus z times z minus y square minus 2x cube. Let us do this. Okay. So, this is what 2y dy minus dz divided by 2y z minus y square 2y square, if I do that. Okay. So, 2y square minus z and what I will get, z minus y square minus 2x cube. Okay. So, what I will do, okay. So, what I will do, this z minus 2y square will cancel with z minus 2y square, we will get dx over x equal to, z minus 2y square will cancel with this, dz minus 2y dy divided by z minus y square minus 2x cube, we get this. Okay. Now, let us put let us take some w equal to z minus y square, then dw will be equal to dz minus 2y dy. So, this will be equal to dw divided by w minus 2x cube, and let us solve this. Okay. So, what I will get, dx by x equal to dw over w minus 2x cube, and what I get, x dw equal to w dx minus 2x cube dx, which I can write as x dw minus w dx divided by x square equal to minus 2x dx. Okay. And this is d of w over x equal to minus d of x square. So, when we integrate, we get w over x equal to minus x square plus a constant C2. Okay. And w is what, z minus y square. So, we get z minus y square divided by x plus x square equal to C2. So, this is another solution, we can write it as bx by z equal to this. So, what we get, one solution is this y over z equal to C1, and the other solution is x square plus z by x minus y square by x equal to C2, and we therefore have this solution, general solution, phi y over z x square plus z over x square plus z over x minus y square over x over x equal to 0. So, this is how we get the general integral for this equation. Now, let us look at last problem of this lecture. Find the equation of integral surface of the differential equation, first order Cauchy-linear PDE 2 by z minus 3 p plus 2 x minus z q equal to by times 2 x minus 3, which passes through this circle. So, let us first solve this Cauchy-linear PDE. So, we have the characteristic equations as dx over 2 y times z minus 3 equal to dy upon 2x minus z equal to dz over by times 2x minus 3. So, these are the characteristic equations for this Cauchy-linear first order PDE. So, you can see we take dx over 2 by z minus 3 and dz over by times 2x minus 3, then by will cancel and we will be able to integrate easily. So, dx by 2 y z minus 3, let us we take dz by times 2x minus 3, then this by will cancel with by and we shall get 2x dx minus 3 dx equal to 2z dz minus 6 dz, which gives us on integration we get x square minus 3x, then we get z square minus 6z plus a constant C1. So, R we can say x square minus 3x minus z square plus 6z equal to C1. So, thus we have ux by z equal to x square minus 3x minus z square plus 6z equal to C1 as one solution. Now, let us try to find the other solution. So, for that let us again try lambda mu nu such that lambda dx plus mu dy plus nu dz equal to 0, where lambda mu nu are functions of x by z. So, what I will do is I will take, let us take lambda equal to 1, mu equal to 2 y and nu equal to minus 2. Let us see this. So, what we will get then lambda dx plus mu dy plus nu dz. This will be giving you lambda we are multiplying by 1. So, 2 y z minus 3, mu is 2 y. So, 2 y into 2 x minus z. So, we get 4 x y minus 2 y z, and then nu is minus 2. So, minus 4 x y plus 6 y, and we can see that this cancels with this, and then here we get 2 y z which will cancel with this 2 y z, and minus 6 y will cancel with 6 y. So, we get 0, and thus dx plus 2 y dy minus 2 dz equal to 0, which gives us on integration x plus y square minus 2z equal to a constant C2. So, we got another solution bx by z equal to x plus y square minus 2z equal to C2, and therefore, the general solution is phi ub equal to 0. So, we can write the general solution as phi x square minus 3x minus z square plus 6z x plus y square minus 2z, x plus y square minus 2z, x square minus 3x minus z square plus 6z equal to 0. Now, let us find the integral surface which passes through the circle z equal to 0, x square plus y square equal to 2x. So, the circle is given by x square plus y square equal to 2x, z equal to 0. And this equation can be written as x minus 1 whole square plus y square equal to 1, z equal to 0. Now, let us write the equations of the circle in the parametric form. So, I can write x equal to 1 plus cos t and y equal to sin t and z equal to 0, z equal to t equal to 0. So, z equal to 0 we get z equal to 0. Now, what we will get, we have two solutions u x by z equal to x square minus we had written u was equal to x square minus 3x minus z square plus 6z equal to C1. Okay. So, this is C1 and then bx by z equal to x plus y square minus 2z equal to C2. Okay. So, if the we have to find the integral surface that passes through this curve, then let us use the characteristic, let us use the parametric form of the curve, that is the circle through which the integral the general solution or the solution of this has to pass. So, x is square minus 3x. So, 1 plus cos t whole square minus 3 times 1 plus cos t minus z, z is 0. So, we get 0 here, here also 0. So, this is equal to C1 and then we have x is 1 plus cos t, the second equation, and then we get plus sin square t and we get z equal to 0. So, this is equal to C2. Now, this let us square 1 plus cos t. So, this gives you 1 plus cos square t plus 2 cos t minus 3 cos t equal to C1 and here what we get 1 plus cos t plus 1 minus cos square t equal to C2. So, simplifying we get cos square t, then we have here minus cos t and then 1 minus 3 is minus 2. So, we get C1 plus 2, C1 plus 2 and here we get cos t minus cos square t equal to C2 minus 2. So, adding these two equations, this equation and this equation, what do you notice? Cos square t will cancel with cos square t, cos t will cancel with cos t, 2 will cancel with 2 and we will get C1 plus C2 equal to 0. Okay. So, C1 plus C2 equal to 0, C1 is this, eliminating C1 C2 what we get, x square minus 3x minus z square plus 6z, that is C1, and C2 is x plus y square minus 2z equal to 0. Okay. C1 plus C2 equal to 0. So, this can be written as x square plus y square minus z square and then we get minus 2x and we get 4z equal to 0. So, this is the required integral surface. So, in this lecture we have looked at the initial value problem for the first order Quasi-linear PDE. In the next lecture we shall look at the existence and uniqueness of the solution of the Quasi-linear PDE, which and we will discuss the Cauchy method to determine the solution of the first order Quasi-linear PDE. The uniqueness and existence problem we shall consider. Thank you very much for your attention.